All right. So in this lesson, we're going to be covering some advanced data visualization techniques. And I'm going to show you how to create 3D charts in Python. So let's start off with a section heading. I'm going to change this to Markdown. And I'm going to use the pound symbol. And then write example 4. Data viz with 3D charts. And in the same Markdown cell, we're going to be playing with a little bit more of the LaTeX notation. Let me show you the function that we're going to minimize. This function will have two variables, so it's both going to have an x and a y, and we'll have to minimize our cost across both of these inputs. So both of these parameters will have to be optimized in order to minimize the cost. So here's what our cost function will look like. So I'm going to add a subheading, and I'll say minimize $2 f of x comma y is equal to, and then I'm going to use the backslash to put in a keyword here, frac, frac for fraction. And then I'm going to use a curly brace, a 1, close the curly brace, and then have another opening curly brace, and then put a 2, and another closing curly brace. And then I'm going to put $2 at the end for my closing tag. And now let me press Shift-Enter to show you what this LaTeX notation actually looks like. So what you see here is that we've created a fraction by using this tag right here. The top part of the fraction is between the first set of curly braces, and the bottom part of the fraction is in the second pair of curly braces. The function that we're actually going to be minimizing isn't 1/2, it is 3 to the power of, and then it'll be another opening curly brace, minus x to the power of 2 minus y to the power of 2. Closing curly brace, and then I'll add 1 at the end. Now let me hit Shift-Enter to show you what this function looks like. Voila. Now a nice little trick with complicated functions like this is that we can split it up a little bit. This also makes it easier to write it in the Python code. So we can also write it like this. We can say minimize $2 f of x, y is equal to, and then have again the backslash, fraction, curly brace, 1, and then another curly brace, r plus 1, closing curly brace, $2, and then where $r, closing $, is, and then another $, 3 to the power of opening curly brace, minus x to the power of 2 minus y to the power of 2. Closing curly brace, and then another $. And what this line of Markdown will nicely do is show us again the difference between using $2 in the LaTeX Markdown or $1 in the LaTeX Markdown. So with that double $, we get that equation centered, and with the single $, we get that notation in line. Now let's write the Python code to express this function. So I'm going to go with the second way of expressing this equation because I think it makes it much more clear and easy. So I'm going to say df f x comma y colon r is equal to 3 times open parentheses minus x times 2 minus y times 2. And then I'll say return 1 divided by parentheses r plus 1. And I'll hit Shift-Enter, and this is what our function looks like in Python. So even though we could have written all of this in one line here after the return keyword, I find it much more readable if we split it up like this. Now let's create a chart with this function. Let's see what this actually looks like on a graph. Now, as always with charts, we got to make some data first. So we're going to use that linspace function again. But this time we're going to create data for both our x's and our y. So I'm going to create a variable called x underscore 4 is equal to np for numpy, linspace, parentheses, start equals -2, stop equals 2, and then num equals 200. And I'll do the same for ry because we've got two variables now. So we'll have y underscore 4 equals np dot linspace start equals -2, comma, stop equals 2, comma, num equals 200. So while we're at it, let's take a look at what the type of x underscore 4 actually is. What type of object is this? And we can see that linspace gives us a numpy array, an nd array. And we can also see the same thing if I move my cursor over linspace, hit Shift Tab, and then I can see here if I press the plus sign and I scroll down, it returns a nd array. Yeah, the linspace function returns an nd array. So I can see this both if I print out the type or if I take a look at the documentation. Now, the interesting thing with arrays is that they have a shape. They have rows and they have columns. So what we can do is we can look at the shape of this array. We can see shape of x array, comma, x underscore 4 dot shape. Yeah, so shape is an attribute of the nd array. So let's print this out, see what we get. So we can see that we've got a one-dimensional array with 200 rows. A mathematician would refer to this type of data structure as a vector. Let's keep that in mind for later and move on to trying to plot stuff. But before we dive into plotting things right away, let's have a quick think about what a plot might consist of. If we look at our previous Python code that, say, generated this plot right here, what we see is that our chart is in fact made up of different pieces that come together for the final product. So, for example, we had our data points that were plotted as a scatter plot on the diagram. And this was separate from the line that was being charted. Also, our plot had other bits of information too, right? It had things like a title and labels and so on. The point I'm trying to make is that we've actually used several different types of Python objects to make our final chart. In this lesson, we're going to be generating a 3D plot that will look something like this. However, to make this 3D plot, we have to start manipulating other types of Python components that make up this diagram. These Python components include the figure object and the axes object. Now, we've already met the figure. Remember how we sized our plot previously? We did that by manipulating the figure's size. So let's come down here. I'll add a little comment, generating 3D plot. And let's size our new plot with plt.figure parentheses fig size equals, and then we'll pass in a list with the square brackets 16 and 12. So this is how we sized our figure always. Now here's something new that we can do with this code. If I hit Shift Tab on this function, then I can see by expanding the documentation and scrolling down that this function in fact returns something. This figure function has an output and it returns, well, it returns a figure, yeah? A figure instance will be returned. And since this bit of code has an output, we can actually store that output somewhere. So I'm going to create an object, call it fig, and set it equal to the output from this bit of code here. So now our figure object is stored in a variable called fig. Now at this point you might be asking, what's a figure? And the answer is, it's a little bit abstract. Conceptually, A figure is just a matplotlib object that allows us to manipulate our final chart in certain ways, like by, say, changing the size or adding axes to the chart. In fact, you can think of a figure as a kind of top-level container that contains other elements in the chart. That's just how the matplotlib library is structured. In their code that we're using, the figure is a container for other bits of the chart. Now, the follow-up question is, what kind of other elements are contained in a figure? Well, one element actually is the chart's axes. And we are particularly interested in the chart's axes because we're going to have to manipulate them. So the axes, we're going to store in a variable as well. So I'm going to say ax is equal to fig.gca, parentheses, projection equals, then the string 3D. So what's happening here is that we're calling a function called GCA, which is short for get current axes. So we're getting the axes from the figure, and we're storing them in a variable as well. So our fig object came in handy here on this line because we're using the fig object to grab our axes. Now, I can't actually run the code like this. If I press Shift Enter, I'm going to get an error. And the error reads value error, unknown projection, 3D. The reason we're getting this error is because we have to import our 3D axes into our Python notebook. So I'm going to scroll back up all the way where we had notebook imports and packages. And here I'm going to add the code from mpl underscore toolkits dot mplot 3D dot axes 3D. Import capital A axes 3 and then capital D. So it's quite a mouthful. We're importing something very specific. So from mpl underscore toolkits dot mplot 3D dot axes 3D import axes 3D. And then I'm going to have to hit Shift Enter on this import. That way we've refreshed our Python notebook. And if I scroll all the way down to the bottom, I can now go to the cell and actually run it. It will recognize our 3D axes and it will actually generate an empty chart for us like this. Okay, I'm going to click back into the cell and add our next line of code. Because now that we've got our 3D axes, we can try plotting our function on them. The method that we're going to call on our axes object, so writing ax dot, is called plot surface. So we're not plotting a line, we're plotting a surface because now we're in 3D space. So we'll say plot surface, parentheses, and then we have to feed our data to it. So we're going to say x underscore 4, and then y underscore 4. And then for our z-axis, our third dimension, it's going to be f x underscore 4, comma, y underscore 4. And then two parentheses at the end. So this is the function that we want to call to actually plot a 3D chart. And we're doing this on the 3D axes object itself. But before I run this, there's still something I have to do. So let me quickly pull up the documentation here by pressing Shift and then Tab on my keyboard and hitting the little plus sign here. We can see in the signature there are 3 required inputs, an X, a Y, and a Z. But scrolling down, we can also read that these 3 inputs need to be 2D arrays. So they need to have 2 dimensions. But let me ask you this. Is X underscore 4 and Y underscore 4 a 2D array, as it is right now? The answer is no. If we look here, our shape that we've printed out is in fact showing us that we have a 1-dimensional array. So it's got 200 rows, but it's only got 1 dimension. So there's something we have to do. We have to make this 2-dimensional. Let me add some more lines on the top here. To meet our requirement for our plot surface function, we have to transform our x_4 and our y_4 to a two-dimensional array. So we've got a one-dimensional vector, and it should become a two-dimensional matrix. And this is where our good friend NumPy comes to the rescue once again. We've got a really, really good NumPy function called meshgrid that we're going to make use of to do just that. So I'm going to type x_4, comma, y_4 is equal to, you'll notice I'm using sequence unpacking here. So x_4, comma, y_4 is equal to np.meshgrid, parentheses, x_4, y_4. So what does meshgrid do? If I look at the docs, I can see that this method returns a coordinate matrix from a coordinate vector. So it will return to us a two-dimensional array given a one-dimensional array. Let's print out the shape so I can prove this to you. I'll say array after meshgrid, comma, x_4 dot shape. Let's run this again. And here we see that our array now is 200 rows by 200 columns. So I can show you what this would look like actually, but I'm not going to show you a 200 by 200 matrix. I'll just show you a 5 by 5. So I'm going to change the arguments here to our linspace function. And then down here I'll say x_4, and we can actually see what it looks like if it was a 5 by 5 matrix. So this still is two-dimensional in contrast to what it was before we called the meshgrid function. This print statement is showing us that here at this point it was still one-dimensional, but by the time we've run meshgrid, it has become two-dimensional. All right, so I'll delete this really quick here, and I'll change our arguments back to 200. And I'll rerun the cell. Now it's time to look at our 3D chart. So let me add plt.show parentheses and hit Shift Enter. Scrolling down, we see our beautiful surface being plotted on a 3D axis just like this. Very nice. So I'm very proud of our creation here, but I think it could use some improvements. For starters, I can't really tell which axis is which just by looking at this. So what we're going to do is we're going to add some labels to our axes. Now here's the thing. Previously, we've added plt.xlabel, yeah, and had a function call like this. But we've got a 3D chart, and so we're going to call our method on our axes object. So we're going to say ax dot set underscore xlabel, and then we'll pass in the string x with a font size equal to 20. And I'm going to copy this code, paste it 2 more times, but instead of the x label, I'll have the y label and the z label as well. And of course, I'm going to change the string to display to y, and then I'll change the z-axis to f parentheses x, y hyphen cost. So that way we'll have a label on all our 3 axes of our 3D chart. Let me hit Shift Enter and update what's on screen. Voila. So this is what the Z label looks like. Here we've got our X label and our Y label. Brilliant. So that's starting to look pretty decent. But you know what? We can make it look even better. And the way we're going to do this is by using color. Adding color provides so much additional information when it comes to data visualization. So my objective looking at this is to be able to visually differentiate, not just based on where things are, if a value is high or low, but what color a certain area is on this chart. I want the color itself to tell me if the cost is high or low. And to do that, we're going to have to import a module called the color map. So I'm going to scroll back up. And in our very first cell, I'm going to keep all the import statements nice and tidy up top. I'm going to say from matplotlib import CM, and CM stands for color map. Now I'm going to hit Shift Enter, and I'm going to scroll back down, and then I'm going to modify this call to our plot surface function. This plot surface function can take some additional arguments, and one of these arguments is, surprise, surprise, a color map. So I'm going to say CMap is equal to, and then I'm going to use the color map module that we've just imported. So I'm going to say CMap is equal to cm.coolWarm. CoolWarm is one of the color maps that we can use from the color map module. So let me update this chart right now by hitting Shift Enter. And there we go. Isn't that amazing? I think this is so cool. But just like with our regular line plots and our surface plots, we can actually add transparency to this plot as well. So we can go back to our plot surface call and add a comma at the end and then provide an additional argument, namely alpha equals, and then say 0.4 to add some transparency. So let me hit Shift Enter and update the chart. Now it looks like this. With the alpha value at 0.4, we can even see our grid shining through on the back of our chart. Now, personally, I think this chart is starting to look quite wonderful because we've got our high cost in red and we've got our low cost in dark blue hues. So we can already visually differentiate between costs that are high and low just by looking at the color. And also, based on similar colors, we can see which parts of our chart actually have a similar cost as well. Now I'm going to end this lecture on a challenge. Can you change the color mapping of this chart? I mentioned earlier that there's quite a few different color maps available, and we've used one of them called CoolWarm. Can you dig into the documentation and change the color map on this chart to something else? I'll give you a few seconds to pause the video before I show you how. And here's the solution. Part of becoming a proficient programmer is getting really good at Googling, and I'll show you 2 pages that you can use to give you some inspiration. So there's this one here, where it's all about choosing color maps. And here you can find the names and the look of various different types of color maps. So for example, one of the color maps is called Plasma. So if I update my code here to cm.plasma, then I'll get a color map that looks like this on my chart. But of course, you're not limited to this. You can also try, I don't know, winter or hot. See what those look like. cm.winter will give us this look, and cm.hot will give us this look right here. Now, if Google didn't bring you to this page, then perhaps you landed on this page instead, the colormaps_reference.py documentation. And here you'll also see very similar information. You'll get a visual representation of various different color maps that are available. So either of these 2 pages from matplotlib.org will give you the information that you need to find the right color map to suit your preferences.